Okay, hello everyone. So in today's lecture, we will continue our discussion about process synchronization. But before doing that, let me give you a recap of what we did in the last lecture. So we were basically talking about what is process synchronization and what is like why we need it. So we need the process synchronization because we have a situation where multiple threads or multiple processes, if they are accessing the same shared data, they can end up having inconsistent data or inconsistent data structure. And the reason behind that having that inconsistent data is that multiple accesses to the same data are not synchronized, they are not controlled. So after studying a try example, we found out that we can avoid ending up having inconsistent data states by uh, by synchronizing the accesses. And for that, we defined the problem of the critical section problem. So the critical section problem is that if two or more processes or two or more threads are accessing the same data, and when we say accessing, it basically mean that at least one of them is writing the data, then we should make sure that the one process or thread can modify the data and all other must wait. And for that, we said that we need to give a structure to our program where we first have the entry code or entry section code. And this entry section code actually ensures that only one thread or process can go through. And after passing through the entry section, a thread can or a process can access the critical section. And after that, it goes through the exit section. And after that, it continues to remainder section of the program, right? So we also had a look at how we can use the Peterson algorithm, which is a software-based solution for implementing the synchronization or to solve the critical section problem when only two threads or two processes are involved, which means that only two threads or two processes are sharing the accessing the shared data, right? So uh, uh, the thing is that this Peterson algorithm, it was able to work in the old computer architecture or on the old computer machines. And when we say the old machines, we mean those machines which doesn't have a specific optimization feature. And what is that specific optimization feature? It is instruction reordering. So what we are necessarily saying is that if we have a machine which doesn't perform instruction reordering, then we can use the Peterson algorithm to solve the critical section problem for two processes. However, if we have a machine which performs instruction reordering, then our Peterson algorithm will not work. But you can ask the question like, what is instruction reordering and why we even need it in the first place, right? So instruction reordering is actually an approach where the orders of the instructions in a program, uh, they are modified by the compiler before the program is executed. So the instruction sequence is modified by the compiler. Why? Because compiler thinks that if it modifies those instructions, or it modify not instructions, if it modifies the order, then it can speed up the execution of the program, right? So let me try to give you an example where instruction reordering can actually uh, give performance benefit, right? So uh, where is one note? Yeah. So week 12, right? So let's say you have this program. I'm writing it in high language, right? High level language. So let's say we have this program which says uh, A is equal to 10, B is equal to 50, and C is equal to uh, let's say 60, right? and then it says if B is less than C, uh, then set Z equal to 10 and set A is equal to A plus 20, and I don't know, maybe there is some other variable y is equal to y plus 50. Okay. Now, in this program, now even like what I can do is, okay, let's ignore these first statements, right? So what we are saying here, we are saying if B is less than C, then Z is equal to 10, and then we after that we have these instruction A is equal to A plus 20 and Y is equal to Y plus 50, right? So actually here we are doing a branch, right? And let's say that at the time point we start executing this instruction here. Let's say I'm like just putting a star to indicate that the current time point, right? So at that time point, let's say we have the value of A in the register. Let's say R1, it is already loaded previously, maybe by the program at this in this before by the instruction before this if statement. And in R2, we already have the value of Y, right? And but value of B and C is not yet loaded in the register, which means that it must be read from the memory. Now if you have a little bit understanding of computer architecture, you know that uh, so if this is your CPU core, right, and if this is your memory, right, and here you have CPU. So in the memory you have the data, let's say B and C, right? So if now you execute B, if you want to execute this if condition, you first must load B and C into some registers, let's say R3 and R4. So B will be loaded into R3 and C will be loaded into R4, right? But since you are reading them from the memory, it will take long time because accessing the memory is expensive, much more expensive as compared to accessing the register. So let's say I'm assuming that reading one of them, like for example, B into R3 take 100 cycles. So it will take 100 cycles for reading B into R3, the next 100 cycle for reading C into R4. And then maybe you also, let's say, need to uh, uh, write the value of Z into memory, right? So let's say that is also taking 100 cycles, right? So it's mean that after 300 cycles, you will be able to execute these instructions, these one, right? But these instructions now, it means that these instructions must wait for 300 cycles and after that they can be executed. Now, in the modern architecture, the modern computers, what happen is that compilers look for instructions which have no dependency. Like for example, A is equal to A plus 20, this statement, and Y is equal to Y plus 50, this second statement, both are not dependent upon B, C, or Z, right? So, and they are already loaded in the register by the instructions preceding the if statement. So what the compiler will do is it will simply reorder the program. So it can write it will reorder it into let's say A is equal to A plus 20, Y is equal to Y plus 50, right? And if B is less than C, and let's say these two instructions each take, let's say, one cycle, right? So if I execute the total program here, it will take 302 cycles, right? So, and then you write here if B is less than equal to C is equal to 10. So now what happened is that these instructions, they don't need to wait for 300 cycles, right? So what you can do is like your computer will, what it will do is that it will issue it will should say, okay, read data from B, right? And while it is waiting for the data from B to become available, it will see, okay, I can do the A is equal 20 because it is not dependent upon B or C, or I can also execute y is equal to y plus 50. So while the data is being fetched from the memory, so instructions will be executed out of order. So when we say out of order, it means the program order is that this instruction, let's say I'm naming it instruction a statement, let's say, not instruction, let's say statement 4 and statement 5. So, and these one are, let's say, statement 3 and statement 2. So according to the program address, statement 4 and statement 5, they are executed after statement and 2 and statement 3. But compiler thinks that if I simply reorder them, I can get some performance benefit. So it executes statement 4 and statement 5 before 2 and 3, right? So it is good. This instruction reordering is good in improving the performance, but then it can also create some problems, right? Uh, so that is what we mean by instruction reordering. So now, how it can create the problem. So let's try to understand. So uh, let's say that you have two threads which are sharing the data, and the data which is shared between the two threads is Boolean flag variable, which is initially set equal to false, and an integer x variable which is set equal to 0, right? And then the thread one, it executes this code while not flag. So if flag is like not if flag is 0, so it will keeps waiting, right? And when flag is set equal to true, then it prints x, the value of x. And thread 2, it executes this code. It sets x equal to 100, and then it sets the value of flag equal to true. So if we have this code executed by thread 1 and thread 2, and we know that flag and x are shared between the two threads, what do you think will be the expected output after executing this code for the two threads, after running these two threads? Anyone who want to answer?
Sorry, what was the question?
So we have two threads, and both share the two variables flag and x. Flag is initially set equal to false and x is set equal to 0. And then thread 1 executes this code while not flag, print x. Note here there is a semicolon, which means that it will keep waiting as long as flag is 0, right? And once the flag becomes true, then it will print the value of x. On the other hand, thread x, it sets x equal to 100, and then it sets flag equal to true. So if that is the code executed by thread 1 and thread 2, what is the expected output when we run the code?
And not flag, meaning flag is false, right?
Yeah, yeah. So as long as flag
So,
is false, it will keep waiting in the while loop. Thread 1 will keep waiting in the while loop.
Would it just be 0 over and over again because it still waits for flag to be true?
Yeah, that's true, but also consider that thread 2 is also running on a different core at the same time.
Oh, okay. So
So let's say you have I'm just writing C0. So thread 0 is running on core 0 and thread 1 is running on core 1, right? So the thread 1 will be, or maybe I can use the
well, since x equals 100 is in front of flag true, wouldn't it just do x equals 1 or print 100?
yeah, that's true, but let me explain. Okay. So
Okay.
let's say we have here core 1 running thread 1 and core 2 running thread 2, right? So we have thread 1 says while not flag, so print x. And here we have code x is equal to 100 and flag is equal to true. And initially we know that flag is false and X is equal to 0, right? Now, let's say if C1 executes this one, it will find flag is equal to false, so it will keep looping here at the while, right? How long it will keep looping? Until on code 2, the thread 2 which is executing, it comes in, it performs the execution, it sets x equal to 100, and then it sets flag equal to true, right? So if it sets, when it sets the flag equal to true, this loop will break, right? The loop will break and thread 1 will print x. So what will be the value? What is value of x? It is set by 200 by thread 2. So the 100 will be printed, right? Is everyone with me? Is that clear?
That makes sense.
Okay. So, however, that was our expected result, right? That is what we want our program to do. However, since the variables flag and x are independent of each other, the instructions for thread 2 may be reordered. Remember, we said that in the modern computer architecture, what happens is that compiler, when you like compile your program, so compiler performs different passes on your code, right? And in one of those passes, what it does is that it looks for instructions, and if it sees some instructions which are not dependent on other instructions, and by reordering them, compiler thinks that it can get the performance benefit, it will execute those subsequent instructions, it will reorder those subsequent instructions. So for example, here what we have here is like in thread 2 code, we have x is equal to 100 and flag is equal to true. Now they are not related to each other. There is no dependency between x and flag, these two statements, right? So compiler may think like in the like bigger picture, in the context of the broader picture, the whole program, here we have only a code snippet, right? If it thinks that by reordering these instructions, it can get a performance benefit, it can possibly change their order. So it can like perform flag is equal to true first and then set x equal to 100. Now, if that happens, what will we will not get the expected output of our program, right? Why will not get expected output? Uh, let me. So why will not get expected result? So let me take this, put this one here, right? Now let's say that our compiler simply reorders the code of the thread 2. So thread 1 is still performing this one. This is thread 1, but the code of the thread 2 is reordered such that it says flag is equal to true and then x is equal to 100, right? Now what will happen is that let's say now this is the execution order. So first T2 gets the chance to run, it sets flag equal to true, right? And then T1 runs. So this loop is broken because flag is equal to true. So the execution, the control flow goes to the next instruction and it prints x. So when it prints x on the console, you see the value of 0. Output is equal to 0 because here we are setting the value, thread 2 is setting the value after that, right? So why is it happening so? Because your flag is equal to true statement is has its order is changed and it is executed before x is equal to 100, right? Or even in there is another case, like there can be another scenario. Let's say the T2 is not, the compiler does not reorder the code of the program of the thread T2. It reorders the instructions of the T1 if it thinks that there is no dependency, right? So what will happen here? Again, 0 will be printed, right? Because whatever initial value is, it is printed here, right? Which is not what we expect. So as a result, what happens that the compiler thinks that by reordering it can get the performance benefit, but then we can, in some situation, we can end up having incorrect outputs as a result of that optimization, right? Now you can ask, okay, what it has to do anything with our synchronization problem or the critical section problem. The issue is that the Peterson algorithm, which we have seen earlier, it works, as I said, in the older architecture, which doesn't have which doesn't support the instruction reordering. But if we run Peterson algorithm, let's say on our today's computer, and our compiler, the instruction reordering is enabled, then what will happen is that possibly the Peterson algorithm will allow more than one processes to enter the critical section at that same time, right? So here is the example of how Peterson algorithm will malfunction if there is instruction reordering. Now I don't know if you guys remember the code of the Peterson algorithm, but I will explain. So we know that shared variable is turn, and then if there are two processes, then there is an array of with the name of interested with two elements 0 and 1 at index 0 and 1, and it is also initially set equal to false, right? And turn is I don't know, it is also initially set equal to some unknown value, right? So now let's say maybe it's better if I show you first the original code of the Peterson algorithm, because then you will be able to differentiate from the version where the instruction reordering is happening, right? So let me go to the original code of the Peterson algorithm. Okay. So here is what we have, like, let's say two processes A and I and J, right? So first what you do is that you set interested is equal to true. Both of the processes set their corresponding elements in the interested array equal to true. Like I sets the process 0 will set the 0th element equal to true, and process I will set 1 will set element at index 1 equal to true. And then process 0 will set turn equal to 1, and process 1 will set turn equal to 0, right? So this is the like normal sequence or normal code of the Peterson algorithm. Now we are going to see that if instruction reordering happens, then how it makes how it fails the Peterson algorithm, right? So I would just to make sure everything runs correctly for the what is happening here. For the project assignment due today, are we supposed to run it on the CS machines? Uh, okay, I can take care of these questions like related to project at the end, okay? Let me focus now on the lecture, but if you have questions related to lecture right now, you can feel free to ask them. At the end, you can remind me to give you like 5 minutes to answer project related questions. Okay. So now let's see how instruction reordering can fail the Peterson algorithm. Now, let's say you have turn interested 0 is initially equal to false, interested 1 is also initially equal to false, and turn has some garbage value, something, right? I don't know. We don't know what is the initial value. So here we are now reordering, right? Reordering the sense like compiler thinks that if it moves this instruction before the interested I is equal to true, it can get performance benefit, right? So what it does is that it does so, and as a result, process 0 executes turn is equal to 1. So now turn is equal to set equal to 1. And then let's say process 0 is context switched out, right? And process 1 is still running. So it sets turn equal to 0, right? And then it sets interested 1 is equal to true, right? And then it looks at this while loop. So what condition of this while says? It says if while interested 0 and turn is equal to 0, then keep waiting. If both of these parts are true, then keep waiting. So is turn equal to 0? Yes, that is true. But the first part of the condition is false. It says if interested 0 is true, right? But interested 0 is not true, it is false. So process 1 enters the critical section, right? Let's say while it is in the critical section and it has still not exited from the critical section, and process 0 is like scheduled again. And then remember, compiler had compiler had reordered its instruction. So now it says, okay, interested 0 is equal to true, right? So it sets interested 0 equal to true here, and then it checks the condition while interested 1 and turn is equal to 1. So for both of these conditions conditions need to be true for process 0 to be stuck in the loop, right? So is interested 1 true? Yes. But is turn equal to 1? No, turn is equal to 0, right? So it's mean that this condition is false. So process 0 will also enter the critical section. Now that is the problem. Now both processes, process 0 and process 1, both are in the critical section. It means that Peterson algorithm fails to ensure the mutual exclusion if there is instruction reordering performed by the compiler for performance improvement, right? Which is the case in most modern architectures. So it's mean that we cannot rely or we cannot trust on the Peterson's algorithm in modern machines. So this is actually the visual, just a depiction of the same thing which I have explained in the previous slide. Like for example, in process 0, the compiler has reordered the instructions. So first turn is equal to set equal to 1, and then flag 0 is equal to set equal to true. And also in between the here turn is equal to process 1. For the process 1, turn is equal to set equal to 0 and flag 1 is equal to set equal to true. And as a result, both enter the critical section at the same time. Okay. So then the issue is that, okay, then how can we solve this problem? We can solve this problem if we use a primitive or a feature which is known as memory barrier, right? So what is memory barrier? So memory barrier is actually a way of providing some memory guarantees to the applications running on a computer. What do we mean by memory guarantees? By memory guarantees, we mean that if the changes are made to a memory location, a shared memory location between two processes. Let's say there is a memory location which is shared between two processes, and one of them make the change. Then the question is that when will that change become visible to the other processes who are also accessing the same memory location, right? So one memory model is known as strongly ordered, where any modification in the shared memory location by one of the processor, it becomes immediately visible to all other processors, right? So for example, in the previous case, for example, let's say you have two cores, right? And the threads running on the two cores, they are sharing a variable, let's say variable x, right? So if the thread on thread 1, it let's say it reads the x from memory and brings it into its register, right? And it makes any change in the variable x, then the other process thread, let's say thread 2, will be notified, or it will be able to see the updated value of the x. before before it can do any operation on the X, which means that it will not perform any operation on the older value of X in the memory, right? So actually, if when the X will be loaded into the registers of X1 and modified, then they will be written back. It will be written back into the memory, and all other processors are the cores in the system. They will be notified that X is modified. Okay. So weakly ordered is the situation where a memory modification of by one processor may not be immediately visible to all other processors, right? So a memory barrier, it is an instruction which forces any change in memory to be propagated or made visible to all other processors. So for example, uh, hmm, actually I think we have example. We have examples, so I don't want to go to one note and how to say uh, rewrite the example. Okay. So memory barrier instructions. So memory barrier instructions, they are performed in systems to ensure that all loads, wait a minute, to ensure that all loads and stores are completed before any subsequent load or store operations are performed. What does it mean? It means, remember, for example, in our previous example, we were saying like uh, x is equal to, what was the code of thread 2? X is equal to 100, right? And then uh, flag flag is equal to true. I'm just writing T for that, right? So now what was the problem? The problem was that compiler was reordering and the instructions such that flag was executing before before the statement x is equal to 100, right? So the if we use the memory barrier and we put a barrier here, then what we are saying is that all instructions before the memory barrier, they must be executed before all the instructions which come or which follow the barrier, which mean that it is not possible for the compiler to to reorder the instructions, right? And as a result, what will happen is that we will be able to see our expected result or the correct result in that toy example, right? Because now even like if there is possibility of reordering the instruction, but once the we put the memory barrier, we are saying that no, don't reorder the instructions across the barrier. So any instruction which appears in our program order after the barrier should be executed actually after all the instructions before the barrier have been executed. Therefore, if instructions were reordered, the memory barrier ensures that the store operations are completed in memory and visible to other processes before future load or store operations are performed. So this actually then solves our problem. So if we could add, so if we go to the same example in the like previous slides, if we add a memory barrier to the following instruction to ensure thread one outputs 100. So here what we can do is that in the thread one, we can put a memory barrier between flag while statement and print text statement. Remember, we said that two things can happen. Maybe the instructions in thread 2 are reordered, or maybe instructions in thread 1 are also reordered. But we do, and in both cases, we were seeing the wrong result or wrong output. So what we can do is that we can put the memory barrier in the code of both thread 1 and thread 2. So we are putting in thread 1 the memory barrier between while statement and the print x. Similarly, we are putting now memory barrier between x equal to 100 and flag equal to true. So now we are saying, no, you cannot execute this statement before the barrier. This is not allowed. And similarly, here we are saying, no, you cannot reorder instruction and you cannot move them across the other side. So which means that flag is equal to true will be executed only after all the instructions before the barrier have been executed, including x is equal to 100, right? So now what will happen? For thread 1, we are granted that the value of the flag is loaded before the value of x. So this will always be executed first, and then this will be executed in context of thread 1. Similarly, in the context of thread 2, this will always be executed first, and then this will be executing after the first instruction, after the memory barrier. And this will solve the problem, and now we'll see the expected result. Now the question is how it can be used to solve the Peterson's algorithm. So if we are now running the Peterson's algorithm on a modern machine, and we want to be sure that in all times or in all execution it correctly solves the it correctly solves the critical section problem, we need to use the barriers, because we don't want to risk the situation where the instructions are reordered and then more than one processes are able to enter the critical section. So for that, we can put the memory barrier between the statement where we are setting here. Actually, the flag is interested, right? The interested variable. I just simply use different names. So here you can use interested, or actually maybe let me do it right now, because otherwise later when you will be reading the slides, you will be confused. Okay, so here now we are saying that this interested I equal to true must be executed, and its execution must be completed before any instruction after the barrier is allowed to execute, right? And same we are saying here. Now these instructions will not be reordered across the barrier, and as a result we will never have a situation where more than one process are able to enter the critical section at the same time. Any questions?
Uh,
Let me just fix this code. Okay. So we have seen like how can we solve the critical section problem using Peterson's algorithm. But then on modern architectures, it can create problem if we don't use the memory barriers. But using memory barriers is like very error prone, because you need to be very careful, and like you need to pay attention when you are writing the code where to put the memory barriers, and it puts a lot of burden on the programmer, right? So there is another way to solve the critical problem using locks, right? So we will see how locks can be used to solve the problem. Uh, So for that, what we do is that we use a variable with the name of lock, which is shared between more than which is shared between two or more than two processes. It can be an integer that can have only values of 0 or 1, right? So lock is simply a regular variable. Let's say you say int lock, right? And then you perform two operations on the lock, which are acquire lock and the release lock. So then when you write the code for a process or a thread, you need to structure the code in the following shape, or in the following form. So before entering the critical section, you have to acquire the lock, and once you are able to successfully acquire the lock, only then you can enter the critical section. And once you are done executing the critical section, you need to release the lock, and after that you execute the remainder section of your program. So by remainder section, we mean the part of the code which doesn't access any shared variables, right? So here we are assuming that only one process can acquire a lock, and other processes must wait in a busy loop. So now this lock can be implemented by using some special hardware instructions. But before talking about those special hardware instructions, let's use a naive approach. And by naive approach mean, let's say we use a single regular variable and we write the code for this acquire lock and release lock functions. So let's say what happens if we use an integer as a lock variable without special hardware instructions. So let's say now we have initially lock is equal to 0 and lock is a global variable, which means it is shared between thread 1 and the thread 2, right? So now let's have a look at the code of thread 1. So here we are saying while lock is equal to 1, keep waiting. So basically we are saying that thread 1, it will not enter into the critical section when the value of the lock is already set equal to 1 by some other thread. But if it is not equal to 1, then it will go ahead and set the value equal to 1. And then it will enter the critical section. And once it is done with the critical section, it will release the lock, and which means it will set the value of lock equal to 0. On the other hand, thread 2 is also doing exactly the same thing. Now, let's consider how this code is not a correct solution and what is the reason behind that. So here we have a statement that lock variable itself is a source of race condition. So how it becomes a source of race condition, let me explain it to you by going to OneNote. Okay, so let me first copy paste this code. Okay, so let's say we have initially, let's say lock is equal to 0 initially, right? And let's say we have thread 1 here and thread 2 here. Now we have the statement while lock is equal to 1, but this statement is written in higher level language. Now when you will convert into an assembly language, it will be broken down into multiple instructions, right? So what are those multiple instructions? So for example, you need to first load the value, let's say in register R1 from memory. I don't know whatever address of lock is. You need to load it from memory into the register R1. Then you are, let's say, comparing it against 1. Like, let me use the AVR assembly. Compare immediate R1 and 1. And then you are saying if they are equal. So if they are equal, so go back to loop 1, right? And if they are not, then you are saying okay, sorry, then you are saying okay, load immediate 0 in R1, and then you are saying okay, store an address of memory address of lock the value of R1, right? So this is like you are actually saying this is equivalent of saying lock equal to 0. Sorry, lock equal to 1. Uh, Let me rub this thing. Right? And this is equivalent of saying while lock is equal to 1, right? Now, yeah, now the problem is that this while lock statement, when you actually convert into assembly, it is converted into multiple instructions, right? So here, uh, let's say what happens is that T1, it says, okay, uh, R1 is equal to none. Yeah, R1 is equal to 0, right? It compares it against the 1 and it finds that it is not equal, right? And so it executes this instruction, compare I R1 1 branch equal L1. This was L1 here, right? Okay, so and now but so it only loads the value of lock into it loads the value of lock into the R1, and before it can go to the next instruction, let's say the T1 is kicked out and our context switched, right? And some other thread start running on that exact core. Let's say thread 1 is running on core 1 and thread 2 is running on core 2, right? And when it is like kicked out at that time, what happens is that core 2 executes. So what it does is that it also reads the value, let's say, from the memlock, from the location of the memory, from the memory location into the R2, right? Which is still, we have not yet, remember, we have not yet changed the R1 has, thread 1 has not yet changed the value in the memory location. So it's mean that R2 get the value of 0, 2, right? And then it says, okay, it's compare against 1. Is it equal to 1? No. So it doesn't go back to the loop, and what does it do? It sets R1 uh, equal to 1 and then puts it back in the memory. So in the memory, it sets the value equal to 1 and then it's entered the critical section, right? Now once it has entered the critical section, let's say at that time point thread 1 is like scheduled again. So where will it start execution? It will start execution here, right? What did it has in the value of in the R1 register? It had the value of the value of the memlock, older value, right, which was 0 at that time. So but that value is still in R1. Now it compares with R1 and it says a value of R1 with 1, but they are not equal. So since they are not equal, so what does it do is that it also sets the value of R1 is equal to 1 and write it into the memory. So memlock becomes equal to 1 and it also enters the critical section, right? Where is the problem? The problem is that here this statement while lock is equal to 1 is not a single statement. When you convert it into assembly, it is converted into 3 different statements, right? So these 3 different statements. So it is quite possible that when thread 1 is done with the first statement, it is switched out, it is context switched or kicked out, and the other thread comes in. When I say the other thread, it means the thread 2, it starts executing its code, and since it is loading the data from the memory, it still sees that memlock is equal to 0. So it thinks, oh, I can go ahead and I can get the lock, right? And I can enter the critical section. And when then thread 1 will come back, it will also see it will start from this point, right? And it will also enter the critical. So the basic issue is that the while is translated into 3 statements, right? Now if this while is not stated into converted into 3 statements, but it is a single statement such that in that single statement we can get the value from the memory location into the R1. Single instruction can do all these operations. What? Read the memory, or not read, let's say, let me use the word fetch the value of lock memory location into the register and test it, which is compare, and then set it back mean like here we are like writing the data back into the memory. So writing the value of 1 back into that lock location. So if we can do that, all that in single instruction, then it's mean that either thread 1 or thread 2 will be able to enter the critical section and the other thread cannot. Only one thread will be able to enter the critical section at a given time, right? So the problem or the culprit is the fact that this lock, while lock equal to one statement is not a single, actually single assembly instruction. It is broken down into multiple single instructions, and we know that if we have multiple instructions, then a thread can be at any time point between two instruction. It is possible that a thread is context switched or it is kicked out, right? Which creates the problem in terms of solving the critical section problem. So that's why that this above code is not a correct solution. And as I said, the lock variable itself is the source of race condition here. So now then how can we solve the problem? So if we want to solve the problem, we need to use special machine instructions. Let me check the time. Yeah, we need to use special machine instructions that can do testing and setting atomically or something like that. What do we mean by that? So we want an instruction which can fetch the lock variable from the memory into the register, check the value of that fetch variable, that lock variable against, let's say, whether it is 1 or 0, and then set the or update the value of that variable in memory. And we want all these to be performed by a single instruction, not by not by different instructions, right? So here the problem is that this operation is performed by different instructions. So here we are fetching the data, here we are testing the data, and here we are setting the data back in the memory. Okay. So, okay. So we need some special machine instructions which can perform all those three steps in a single instruction. So we have the modern computer architectures or modern machines, they actually provide you those atomic instructions or non-interruptible instructions. And an example of them is test and set instruction, which actually tests a memory word and then sets its value based on the result of the test operation. And another instruction is compare and swap instruction. I will explain both of them. So hardware ensures that they are executed atomically in a multiple processor environment, which basically mean that only one CPU at a time executes those instructions. Just like, for example, remember we said that if you want to write a value into count variable, so let's say that uh, you have thread 1 and thread 2, and both want to perform x is equal to, this want to perform x is equal to 1 and this want to perform x is equal to 2 at the same time. Both issue the write operation. Now what will happen? Memory will allow only one of them to write the data write the variable x at any at the same time. Both of them cannot write at the same time. Only one will go ahead, the other one will be blocked. So if t1 is allowed, x1 will be set equal to 1, and then if t2 is allowed after t1, then it will come again and overwrite and set it equal to 2, right? But both are not able to perform the write operation at the same time. So it's mean that write operation or store operation is atomic. Store is atomic, right? Atomic mean that it cannot be broken down into multiple steps, right? Only one, it is a single step and step instruction or a single operation, and only one thread can perform write on a given memory location at a given time. So in the same way, test and set instruction and compare and swap, these are also atomic. Atomic mean that only one thread or a one processor can execute them at the given time. So for example, uh, so for example, if I have, let's say, T1 and T2, and both want to do test and set, I will explain what is test and set in a bit, but I just first want to focus on what we mean that only one process can execute. So if they both of them issue this test and set instruction or want to execute the test and set instruction at the same time, again, what will happen that underlying computer hardware, it will allow only one of them to continue. Either T2 will be blocked, which means that X will be allowed to execute, like access the memory and perform the test and set operation on X. And then once it is done, then maybe test thread 2 will be allowed to perform test and set on X. So both can, like, let's say, I don't know, when test thread 1 perform test and set on X, let's say it sets it leaves the value behind of 10. And when test and set on set X is performed by thread 2, let's say it leaves behind value equal to 11, right? So but both cannot execute this instruction at the same time. Okay, so that's why we say that test and set is also atomic, just like store. And same is the same thing is true for the compare and state instruction. Now let's have a look at what these instructions actually do. We know, for example, what is the meaning of the store instruction. Store instruction means, right, put some data, some value at a given memory location, right? So now what does it mean by performing test and set on a given memory location? So let's have a look at that. So this is like this is the definition of the test and set instruction. Remember again, this is here we are writing the code only to explain how test and set instruction works, but otherwise test and set is actually an assembly instruction. It is a single instruction. So like, just like, for example, in AVR microcontroller assembler, for example, assembly language, you write load immediate R1 10. So this is a single statement, a single instruction, right? So, and similarly, test and set is also a single instruction. It is a single assembly instruction. But here we are giving this pseudocode to explain how test and set for assembly instruction works, right? So just like, for example, if we say store X, so similarly, when we say test and set, we will have address of a memory location, for example, target, right? So what it does is that it gets the current value of that memory location into some variable. Again, this is just understanding. No variable will be created, but at abstract level, we are just trying to understand how test and set works. When you will run test and set instruction, no extra memory variable with name of RV is created. It is not created, and it is a single step instruction. Okay. So, but at the higher level, for our understanding, what happens is that it gets the current value of that memory location, and it sets that memory location equal to 1 and returns the old value, right? So, for example, let's say we have X is a variable, right? Which is, let's say, initially has value of 0. Now, if I say, I'm just writing test and dash to indicate test and set, okay? If I only say test and set X, so what will happen? This is single assembly instruction. Hardware will go and check the value of this memory location. Its value is 0, right? Then it will set its value equal to 1 and return the value of return the older value of X, which is 0. And by where it will return? It will return in a register. So how you call it in assembly, how you use it, like this: test and set, and then you specify a register and the address of the lock location. So for example, I am writing only test T and S. to indicate test and set, and I say okay, register 1, and then I specify the location of the variable. For example, I know, let's say I know the address of that variable, I don't know, 0xf0. So again, let's say this is address 0xf0 in memory, right? And let's say it has original value of 1, right? Now when I will execute this instruction, what will happen? This instruction will write 1 into this location, right? And in the register R1, it will put the old value. So at the after the execution of this instruction, R1 will be equal to 1. But if the old value was 0, then R1 will be set equal to 0 at the end of this instruction execution. Okay. Is it clear how test and set is working? The operation of the test and set, again, I'm saying it again and again, this is only a higher level abstraction or pseudocode for understanding the operation or the working of test and set instruction. But in actual code, test and set is simply an assembly instruction, a single instruction which cannot be broken down into multiple operations or multiple steps. Okay. So now now we know what is test and set instructions. So how can we use the test and set instruction to actually solve the critical section problem without without having a situation where multiple threads or processes can enter the critical section at the same time, just like we have seen in this example, that this code is not correct. Why? Because while is broken down into multiple instructions, and as a result, it is possible that multiple threads can enter the critical section at the same time, right? So how can we solve that problem using test and set? So for that, what you do is that you can now simply write the code while test and set and lock, and then after that you will have critical section, and once you are done with the critical section, you will have lock equal to 0, and after that you have the remainder section, right? So how it solves the problem, let me try to explain. Okay, so let me use just a different color. So let's say we have T1 and T2, right? Now both will use this same entry section code and exit section, right? To enter the critical section and to leave the critical section, right? So now let's say initially our lock variable is equal to 0, right? Now let's say both try to execute test and set while test and set and lock, right? And here this also executes while test and set and lock. So, and you know what is meaning of ampersand lock? It's mean the address of the lock. We are giving the address of the lock to test and set, right? Now, remember I said that only one uh, thread or a one process will be allowed to execute the test and set at a given time, right? We don't know which one of them it is like it is decided arbitrarily. There is no like mechanism to give priority to thread 1 or thread 2. Sometime maybe thread 1 will be given access, or it will be allowed to execute, and thread 2 will be asked to wait, and maybe in another situation thread 2 will be allowed to execute and thread 1 will be asked to wait, right? So let's say we assume that thread 1 is both execute this at the same time, right? Now, and then what will happen? Let's say thread 1 is allowed to continue, allowed to execute, and thread 2 is asked to wait. So if that is the case, now remember what is the functionality of the test and set. It sets the value of, it will set the value of the lock equal to 1, right? And it will, wait a minute. Yeah, it will set the value of lock equal to 1 and then return the old value, this one, right? So when it will return the old value, it will be, old value will be 0 here. So now the condition inside the while bracket, it becomes 0. So while will be broken and this will enter the critical section, right? Now remember we said that T2 will ask to wait. So T2 tries the test, and after like T1 has performed test and set, T2 is allowed to perform its test and set. So when it performs test and set, what it will do? Let me just change the color. So it will also write the value of 1 at the address lock, but it will get the older value, which was 1 in this case. So here it gets 1, 1 is returned. So while true, so it gets trapped in the while loop. So it will again and again, it will again try, okay, again it will perform test and set, and again it will set 1 here, and the older value will be returned. So again the while loop is true, so it will be again stuck in the loop, and again it will write 1, and again the older value will be. So it will continue waiting. How long? As long as the value of the lock is not set equal, it doesn't become 0. When will it become 0? When thread 1 will enter the critical section, and after it is done with the critical section, it exits. At exits, what does it do? It sets lock equal to 0, right? So let's say it sets lock equal to 0 now here. It said, okay, lock equal to 0. So now it is 0 here. And after this, if now thread 2 tries test and set again, it will set 1 equal to, it equal to 1 and return the old value. When it returns the old value, it gets 0 here. The loop is broken and it enters the critical section. Only one can enter the critical section at a given time, right? Any questions? Oh, sorry. Where is, yeah. Any questions? Please be like, if you have any question, please let me know, because your next project 3, it is project next module, or not next module, I guess the project 4 or module A or project 3 module B. One of them will be about process synchronization, okay?
Okay.
And they possibly ask you to use test and set or compare and swap instruction, which we are going to see in the next slide. So if you have a question, please ask me. Okay, so I am not going into assembly language version of the same code, but you can necessarily see the same thing I have explained to you earlier. Like if you are doing test and set it, so it will perform this test and set operation on the lock and return the value in the register. Then you are comparing the register value with the 0. If it is equal to 0, then you continue, you enter the critical section. But if it is not equal to 0, is 1, the value which is returned is 1, you test it again. So here it is just a loop, jump not equal, entry section. So you keep checking again and again, okay? And exit section is simply you are putting 0 in the lock. Someone, I guess, messaged, if we are not allowed, okay, if we are not allowed to run it on the CH machine, can we have an extension because we need pseudo permission? My team is having the same problem. Should okay, now I guess I can take your questions on the project. I guess we have only 5 minutes left. Okay, so please unmute yourself and let me know what is the problem.
Yeah, so the issue that I'm having is since we want to like pin it to the one core, we have to use a specific function called Let me see. It's called like pthread set scheme param,
Yeah.
and it's asking that the operation, like when you run it, like it says that it failed and the operation is not permitted. So we need to have sudo in order to run it. So I was
Oh,
just thinking of like having like just like making a VM and running it there.
don't you have your own laptop or your desktop?
I think it only works for Linux, right?
Uh,
That's because I'm
it it can work also in like MacBook or MacBook OS or in Windows, but you know the pthread library APIs there will be different. I have not written the code for other operating systems, so yeah, I'm not sure. But it should work in the virtual machine because I also don't have Linux on my laptop. I have virtual machine, so I am also running those project codes on the virtual machine.
so we should just run it on a VM, is what you're saying.
Uh,
Because
yeah, yeah. If you don't have like Linux on your personal computer, then I think there is no other option.
okay, and then would we be allowed like an extension just for
Uh,
this issue?
okay. Uh, yeah. How many people are there other people also running into the same problem? My team is having the same problem. Sudo is required to pin the. Is there anyone who didn't face this problem?
I I think my group, so like my partner has a MacBook, so when they run the code they're not exactly having that issue, but I'm on Windows and I'm SSH'd into a CS machine and it when I try to it compiles fine, but when I try to run it, I think
Mm-hmm.
you need to use sudo and then
Okay.
dot slash and then the file name.
Yeah, we just don't have sudo access on the CS machines.
Okay. Are you sure that this sudo access problem is stemming from the API call pthread set schedule parameter? Can it, can anyone respond to that? I mean, are you sure like is all those people who are facing the problem, do all of you think that it is because you are calling pthread schedule param or is it possibly because of some other issue?
Well, for me, that's where the error is coming out from.
Okay, so
Me and my teammate are pretty sure that's where it's coming from too, from what we've been testing and what we've looked up real quick.
okay, so what you can do is then okay, uh, today is Wednesday, right? No, Tuesday, right? So if I give you extension until Friday, will that be fine with everyone?
Yeah, that sounds good.
That'd be awesome. Thank you.
Okay, anyone who has an objection or who thinks like until Friday it is not enough? Okay, so then I will extend it until Friday. And what you can do is like as I said, I also don't have Linux. I have virtual machine. So install virtual machine on your personal laptop or computer and try doing the running the code there. Okay. Anything else? No? Okay, if not, then let's stop here and next time we will continue with compare and swap instruction. It is also another atomic instruction which we can use to solve the critical section problem, but we will see the details in the next lecture. Okay, thank you everyone.
Thank you. Have a good day.
You too, have a nice day.